science. One of the major science organizations in the world is NASA. NASA once sent a spaceship to Mars to study the Martian atmosphere. It cost us $193 million to make this spaceship. That was back in 1998. In today's dollars, it's close to $300 million to make this particular spaceship. We sent it to Mars. It was moving at 3 miles a second. Not 3 miles an hour, 3 miles a second. It was going very fast. Still, even at that kind of crazy speed, it left in December 98. It did not get to Mars until September. Come on, smart board. Until September of 99. It still took 9 months traveling at 3 miles a second to get there. But what it's sort of famous for is that when it got there, instead of sending back data, it didn't send back anything. There was no signal from this thing. And after a day or two, they're like, it got lost. And the question was, what happened to the Mars Climber Orbiter? Was it attacked by Martians? Sadly, no. That would have made for a much more exciting past 10 or 20 years. If that had happened, oh my God, would our lives be different if we were like, oh, the Martians are fighting back against our satellites or something. Instead, what they discovered, after about a week, they realized peer-reviewed preliminary findings indicate that one team was using English units while the other used metric units for a key spacecraft duration. The guys at NASA assumed the speed was in kilometers per second, and the guys at Lockheed Martin who made it, the American engineers, put it in there in miles per second. And so they didn't know, and they're like, okay, we got to slow it down, we're getting close to the atmosphere. They had the wrong reading for things. What does this matter? This influences the title of our notes. The title for your notes today should be, If You Don't Write Down the Units. If you don't write down the units in science class, how bad could it be? Well, if you don't write down the units, it could cost America $300 million. Yeah, write that down. That's the title of today's notes. The importance of writing down the units. And we're trying to get you habituated as young science students to writing down the units so that when you're an engineer at Lockheed Martin 10, 15 years from now, you remember to put down the units so NASA doesn't crash the next Mars Climate Orbiter because no one knew what units the ship's controls were in. So that's your title. If you don't write down the units, it could cost America $300 million. Got all that? What unit system do we use here in America? American? We don't actually call it the American. It's called the Imperial or English system of units. Okay. What sort of system does the rest of the world use? Metric. Or the System International. We're going to get into that today. Be sure to say this with a French accent. System International. Well, first of all, let's be clear that I'm exaggerating a little bit when I say the rest of the world uses the System International or metric system because, in fact, Myanmar and Liberia both use the imperial system too. So we're not the only country that does this. There are 2 other countries in the world. Liberia, where my wife was in the past month, was a colony that the U.S. founded for slaves. We wanted to solve the slave problem. Let's ship them back. And we made this continent and a country and tried to send people there. So they're still using American systems. That didn't really work out as a solution. We still had to have the Civil War. So here is why most people don't use the imperial system. Here are a few conversions within the imperial system. There are 4 poppy seeds in a barley corn, and there are 3 barley corns and an inch, and 3 inches in a palm, and 2 palms in a shaftment, whatever that is. Okay? These are all things that date to old English markets, where they're measuring fish and pigs and being well, let's see how many hands high, or how many cubits that thing is. When they're trying to like weigh and measure things, and they have all these crazy like words. I mean, if you think about quart, we've gotten used to, but that's kind of a weird word, like pottle, okay, which is another unit of volume in the imperial system. So all this stuff is very like challenging conversions. Let's ask you. Don't tell me what the answers are. Tell me. Raise your hand if you know how many fluid ounces in a quart. Raise your hand if you're confident about the number of fluid ounces in a quart. Let's see. We got 2. Maybe 2.5. You guys grew up in this system, and all your analogies have it on the side, and only 2 out of the like 17 of you guys know how many fluid ounces are in a quart. How many milliliters are in a liter? Raise your hand if you know how many milliliters are in a liter. All right, 1, 2, 3, 4, 5, 6. So 3 times as many people know the metric system, which we did not even grow up in. All right, people who are guessing, how many fluid ounces in a quart? How many fluid ounces in a quart? It is not 16. It's not 8. It's not 4. This shows us how crappy the metric system is. Indeed 32. Hey, that was my 5th guess. Okay, how many milliliters in a liter? 1,000. Million's a good guess. Okay. Let's play this game again. And let's just see how many people know, just again by show of hands. How many ounces in a pound? If you know how many ounces, don't yell out. How many people know the number of ounces in a pound? 1, 2, 3, 4 people know. 5 people. 6 people know that. Maybe 6 or 7 people. Okay. How many milligrams in a gram? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12. That number should be going up. All right. How many ounces in a pound?
16.
16 is correct for that. How many milligrams in a gram? 1,000 again. Okay. And this is one thing that is clearly better about the metric system is when they use the same word, it has the same meaning. Like in the English system, the same thing, ounces, is not the same like fraction that it is. Milli means the same thing, whether you're talking about liters or gallons or grams or whatever it is. Okay, last pair. How many barley corns in a yard? Raise your hand if you know that. Oh, nope. 108. Okay, so nobody knows that. How many, raise your hand if you know, how many millimeters in a meter? This should be getting more widespread. We should be increasing our number here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Good. In general, it's going to be the same thing. It's going to be 1,000. And that's what's nice about the metric system is you learn that prefix once and it applies in many cases. Oh, there's 108 barley corns in the yard. Double conversions, like the barley corn to yard, are even harder in non-metric systems. Okay, you might know how many ounces in a quart, but then going from that to gallons gets terrible. Here's an example. Inches, there's 12 inches in a foot, and there's 5,280 feet in 1 mile. So if you multiply those, that's going to give you the number of inches per foot. Anybody know what that is? None of you can do this in your head, of course. But if we look at the metric equivalent, the centimeter is about the same thing as an inch, okay? And the kilometer is about the same thing as a mile. There's 1,000 meters times 100 centimeters. What's 100 times 1,000? 100,000. And you guys could do that without a calculator. This, doing a conversion in English systems, requires a calculator. This is hard. Okay? This is not like an intuitive system. Where did we get this crazy system from? Where did we get the foot from as a unit of measurement? Whose foot was it? Because feet vary considerably. Okay? It was a king's foot. Close. It was a Holy Roman Emperor, King Charlemagne V, who said, "Here, peasants, here is my foot. Make this the basis of our land forthwith." Okay? So some king took his foot and said, like, I want this to be the base of everything. What is the small unit that got divided into? Inches. How many inches in a foot? 12. If you have 17 and a half feet, how many inches is that? Hard to do. Why do we have that as a base 12 number? Instead of it being like 10 inches in a foot, we could have made it 10, and then it would be, 17 and a half feet, that's 175 inches. Okay? But it's not that simple. Why is that the base? Why is it 12 units instead of 10? Nope. They divided the foot into certain segments, and they chose to divide it into 12 segments to define the inch. Why? What else is base 12? The months in the year. 1 year goes into 12 months. What else is base 12? The time. What other time unit is base 12? There's 12 hours in what? Yes. There are 12 hours in 1 day. There are also 12 hours in what? 1 night. And back in the day before electric light, those were very distinct times. Like the night was 12 hours long and the day was 12 hours long. We kind of let those run together because we can like stay up or whatever, but back before electric lights. And it goes even further. What is the hour divided up into? How many minutes? 60 is a base 12 number. Right? 60 is 5 chunks of 12. And the minute being divided up into 60 seconds, that's weird and awkward if you think about it. To have 60 instead of like 20 or 50 or 100. Okay? If you have 3.5 hours, how many minutes is that? Hard to do. If it had been 100 minutes in an hour, there's 3.5 hours, that's 350 minutes. That would have been an easy conversion to do. Okay? Why did they divide time up into base 12? Why do we get this crazy 12 in our lives? Not the Greek gods, the Mesopotamians. Why did the Mesopotamians divide time into units of 12? The first one you gave me is the clue here. There are inherently 12 whats in a calendar year? No. 12 lunar cycles. There are 12 full moons every calendar year. So astronomers in Mesopotamia astronomers in Mesopotamia were some of the first people to do math, and some of the first people to write down numbers. Some of the first written scripts come from the Tigris and Euphrates rivers, the clay tablets there, and they needed to be able to predict when's the right time to plant again, when will the spring rains come. That kind of large-scale agriculture required an actual functional calendar. They were the first people to say, all right, there's we can predict it every 12 full moons. That's when the geese are going to return or whatever it was that was calendar based. So the astronomers in Mesopotamia developed base 12 calendars and base 12 time, and we are stuck with that today. Because that worked well in Mesopotamia for predicting when to plant the millet, we are still using base 12 for the inches in a foot. When did we get out of this? Okay? When and where did the metric system come from? It was Europe. What country in Europe specifically developed the Système International? France. What period in France did they decide to come up with a better, more rational system? The French Revolution, the French Enlightenment period. Okay. In the French Enlightenment, they said, let's stop basing our things, these not based in royalty, but in reason. Let's not have these arbitrary things where King Charlemagne's here, peasant. Let's have something that makes some logical sense as our basis for measurement. Because King Charlemagne's dead by this point. And if they wanted to check the foot to see if the foot was the right measurement, they couldn't do that. And these people in the French Enlightenment, they had just come through the Renaissance. In the Renaissance, they did a lot of reading of the ancient Greeks and Romans. They knew that those civilizations had fallen apart. and they knew that the Greeks had measured the world and predicted that it was round, and they want to know how good of a measurement did those like ancient peoples make when they tried to measure like the circumference of the earth. And they went back to a guy named Ptolemy who had measured this like angle of the sun at various places and the distance between them and tried to figure out like what the total measurement would be. But his was based on something called stadia, which was the distance around a stadium in ancient Rome was what the Romans had used for a while. And they tried to look at that, and that was based in miles. Where did the mile come from? Race? No, that was where on the board. The Romans had the mile, and it was based on a Roman legion walking 1,000 paces. A pace is every 2 steps, so like every time 1, 2, and they would walk and they would march as this like group of 100 guys. And they had to 368, 369, 370. When they got to 1,000, one of the guys would stop and plant a stick in the ground and be like, "All right, that's been a mile." That is where the mile came from, was what a Roman legion could walk in 1,000 paces, and they would mark those off. And there are still things in like Europe that have these super old like Roman numeral mile markers from like where Romans put, instead of sticks in the ground, like stones in the ground. The problem with that, what might be a problem with the mile as being based on how far someone walks 2,000 steps? Yeah. It can be different every time. Why? My step and Gemma's steps are probably going to be fairly different. What else might change even if it was me all day long? My speed. I'm going to get tired. Like my morning miles are probably going to be longer than my afternoon miles. If I've done 20 miles, all of a sudden my pace is probably going to like be reduced, and you can't like necessarily count on this as a unit of measurement. There are a bunch of different like miles out there that were like, which mile is the mile, when they were trying to like first standardize these numbers. The people in the French Revolution knew this, and they knew that like it had gotten screwed up over time, and they wanted to try and find a system that would not only like unite the country in terms of weights and measurements and stop having this poppy seed barley corn nonsense and have a more consistent thing, but they wanted one that would be consistent throughout time. That if our civilization, it's incredibly forethoughtful of them, if our civilization fell apart and someone was digging us up and reading our manuscripts, they could find out what our measurements were. They wanted something that would be the same like 10,000 years from now. What is something that they could use as a distance that would not change in 10,000 years? Say again? 10. It is base 10, that is true, but that is not what their base measurement was. What could they measure that would be immune from change? Time, a distance that they could measure on the earth. This stick right here. Archaeologists could find this stick 10,000 years from now. That's what they came up with as their final measurement, but they got it from the entire earth. They couldn't find a distance they could count except the distance from the equator to the North Pole. They said that is not going to change. And scientists or aliens could come here 100,000 years from now, find our records, measure that distance, and know what we meant by the meter. It's again very forethoughtful. Like if our society falls, how could people find our information? How do you measure the distance from the equator to the North Pole precisely? Walking is hard. Okay? What they did is they did a lot of trigonometry. They measured the distance with like chains precisely between various towns, and then they did a bunch of cosine, sine, tangent, a squared, b squared to figure out what this line would be. And this was like a big scientific endeavor, like us going to Mars, the climate orbiter. They measured the entire what's called meridian of Paris by doing a bunch of trigonometry through the Alps to find out exactly what that distance of a straight line up and down along that would be. And they said, all right, we've measured this distance really precisely, and that's like 3.72 degrees out of the total 90 degrees that it must be from the equator to the North Pole. That's got to be a 90-degree angle. And we've measured whatever this fraction of it is. And so we can just multiply by a ratio and get what that total distance is. So they measured one part of the distance, they knew how much angle that was, and they could figure out what the total distance would be. And it was big. And so what they did is they took the Earth, and again, from the North Pole to the equator, and they divided that distance by 10 million. And that gets you down to this nice human scale thing of 1 meter. That is the basis of the meter system or metric system is 1/10 millionth of the distance between the North Pole and the equator. And that is something that is not ever going to change. So that got you the meter. For reference, Joe and I are about 2 meters tall. Most of you are probably like 1.6 meters tall. Most people are between 1 to 2 meters tall. That's just like an easy reference of like most people will be somewhere between 1 and 2 meters. We won't do a lot of meter work in here. We will instead take that number and divide it again by 100 to get the centimeter. Okay? And that should make sense to you as like century. And you've seen these things in elementary school. These are like bleep, 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 bleep. Marks along here are centimeters. Again, there will be maybe 2 or 3 times during the year when we will use centimeters in here. A centimeter, and I will just admit that you guys know Imperial better, it is 2.54 centimeters equals 1 inch, which is about 1 knuckle on your hand. Okay? So if you look at like a knuckle between 2 spots, that's about 1 inch. So divide that by 2.5, and that's about what a centimeter is. Mine's probably a little longer. I'm a nice full 3 centimeter knuckle because I'm a big guy. Most of you guys are going to be a little bit smaller and be close to 2.54. Okay? That is the basis of like measurement in metric stuff. That gives us, let's see, one piece. If we want to get the full volume is